But no, I know the first week is always like the longest week, and just getting in the rhythm of everything. Hopefully the other classes are going smooth. Just again, advice for everything, like even like what I would recommend, like practicing it, segmenting your time out. Like this is a set time I'm going to use for this class. This is a set time I'm going to use for another class. Whatever, you guys are adults, you understand that. But just getting into those rhythms here as your student. So when you start working full time and you get with these tasks for different projects and everything, it kind of helps make that out. Does anyone use your like Outlook calendar at all? Do you guys use that at all? Yeah. Yeah. I mean, if you're using it for work, like use it for school. It's super helpful too, you know, just be like, this is going to be a time I'm going to sit at a coffee shop and practice whatever geotech problems, review stuff, you know, segmenting it out really helps. And this is the time to do it before your schedule gets super caked up with a bunch of other stuff. All right, before we get started on our first little bit of soil composition part one, Canvas, has everyone kind of gotten a chance to familiarize yourself with the Canvas page? I'm sure Dr. Islam's page looked very similar to mine because it was probably the same thing. So you guys are probably used to where all the links are and stuff. Thank you for everyone who submitted that first assignment. I think everybody did, so thank you to everybody who did that. One little piece of news for Canvas, at least. I thought I posted the slides on there, but I didn't post them until maybe last night. I can't remember. So under the lecture notes, or if you go to files, you'll see lecture shells or lecture slides. That's where you can download the PDF. I promise I'll be more proactive next time, and you'll have them the week before, just so you can download them or you can print them if you still have a printer, and you can bring those to class beforehand. Other thing on there, just as a refresher, and you'll see on the next slide, I have this too, but lab is going to start not tomorrow, but the next week. So we will have no lab sections tomorrow. You should be able to view your lab groups now. If you go to people, and then up at the top, there's a little tab. That was chosen specifically, your lab groups were chosen specifically based off of the little automatic button that I press. So everything was randomized. That's always a point of contention. I know some people want to pick their groups. I know some people want to, like, you know, you're used to working with people from last semester. But I do that randomization intentionally because, like, you're going to get placed working with a bunch of randos when you start working. You know, even the hiring manager, a lot of times, like, you might get to know them, and then you start working. They're like, oh, actually, we have demanded another spot. So right now, like, I want you guys to practice working with people you may not normally be comfortable working with. So learning how to adapt with other people's schedules, learning how to adapt with other people's, you know, procrastination, like, limits and everything. And just know too, though, if there is something that happens where, like, hey, I've gave it a shot, I just can't work well with these people, then please bring that to me ahead of time so we can get that figured out. But please just let's try the random groups here for now. And if we need to make changes midway through the semester, we can. Please be proactive again in communicating. And also just remember, everyone's dealing with different schedules, different timings. So please show some patience and some grace to your classmates in that. All right, let's talk about week 2 news and updates here. So I just said all of this, but here's the bullet points associated with that. So they will be starting next Wednesday. They will be starting like right on time, because I don't know if you saw the schedule. For whatever reason, UNF is just like squeeze everything super tight in. So like the lab sections, there's only like a 10-minute buffer between one of the 2 lab sections. And Jonathan is going to be his first time teaching it. I'm going to be helping him a lot, but you know, it's just a lot of prep and stuff. So we're going to be starting like right on time. So please be sure to be there, be seated, and we'll get started like right on those times on Wednesday and on Thursday. Aside from that, let's see. Yeah, our quiz 1 is going to be this week. So we'll have our first like formal legitimate quiz. Remember, those quizzes are based off of today's lecture and then on Thursday's lecture. So after Thursday, I will publish the quiz. It's usually like 5 to 6 to 10 questions, multiple choice or short answer. It's all based off of the content. If you're awake, if you're paying attention, if you're filling in notes or at least writing in notes, you should be fine for those quizzes. And again, me spieling here, like, use these quizzes as kind of a benchmark for your understanding through the class. You know, don't just like copy your friend, or don't just Google all the answers. I know how the internet works. Like, it's easy to do that. but use these as that like kind of like test originally, so you know you're not caught off guard when it comes to the exam time. All right, other little piece of news here. I know some of you guys are already in ASE and interested in that, but if you have heard about or you want to learn more about the ASE Southeastern Symposium, that's where we do the concrete canoe. That's where we build that little house, the steel bridge. Used to build a steel bridge. Bunch of other fun competitions. ASE is having a interest night tomorrow. And it's at 6 p.m. to 7 p.m., which is right button up to my bedtime, so I'm not going to be there. But is that the right room? Okay. Building 4, room 2308. Long story short, again, every year ASE, the student group, gets to travel around. This year it's going to be in the University of Georgia in Athens, so Creature Comfort Brewery up there. Ooh, I cannot wait. I'm going to be there nonstop. But it's a lot of fun. You work with like 17 other universities and you guys get a chance to go and compete and build relationships, blah, blah, blah. A lot of fun. Definitely recommend doing that. So show up tomorrow if you're interested. Because that is in what, March 2nd or March 3rd? Just kidding, March 6th to the 8th. I'm glad you told me that. It's on our syllabus too, but that's when the actual conference is. So if you want to go, we have to get you like your information so you can actually come. All right, another little fun thing coming up. This spring, we have a project coming up with some funding that allows me to hire some undergrad students. So if you've ever been interested in what it looks like to be an undergraduate research assistant, especially one on more of a hands-on practical kind of project that is really involved in the community, then I'd love to talk to you more about it. Basically what we do through the spring and summer and potentially fall, we offer these after school programs at some of the local elementary schools where we just do different geoscience and geoengineering tests. So we do like erosion models. They build like a little engineering thing. It's a lot of fun to see the kids kind of like apply the things that they're learning in the classroom. I am looking to hire at least 2 positions in this. So if you like working with kids, if you like working with your hands and building things, and you have the ability to meet in an after school program around 3 to 5 p.m., then please contact me and I'd love to share more information about it. These types of things too, I don't have to tell you guys this, you guys know the job market is good anyways, but these types of things really help you kind of like be set aside from a bunch of other resumes, because I don't know if you notice, engineers aren't like known for being like social and aren't known for doing a lot of like outreach stuff. So if this is on a resume, whether you're looking at grad school or whether you're looking at a job, you know, this is something that a lot of employers really, really value. And you get paid too. You pay like $20 an hour for that. So it's not a lot of money. I'm sure you guys can make more in the industry, but it's a fun event. And yeah, send me a contact or send me a message on Canvas, or talk to me briefly after class and I'll get your resume and get you plugged in if this is something that's interesting to you. All right, let's talk about geotech stuff. So today we're going to be recapping a lot of geology. Has anyone taken a geology class? All right, a few hands. All right, you guys are way ahead of me because I never even took a geology class when I was in college. I really wish I did. You guys are all smart engineers, so you probably recognize this already. Like the prefix of the word is the same, right? Geology, geotechnical engineer. Has anyone put those 2 and 2 together yet? Yeah. I know. It's pretty, yeah. So stay seated. I know you guys are mind blown. So we talk about a bit, like a lot of the similar things here. We're talking about the study of earth materials. Now, but remember, I said this last class, that technical side of thing, the geotechnical, that just means we apply math to it. Where geology more looks at painting the story, more looks at painting it from like an art standpoint. It's kind of weird. It's like one of the only degrees that is an ist at the end, but it's a degree of art. So anyways, it's important for us as geotechnical engineers to still have a background in geology, but a lot of these things you're going to be familiar with, hopefully, like what is sedimentary rock, igneous rock, and everything. But what I want you to start thinking of as we go through all of this stuff and recap it, how does this affect us as engineers? So like how the soil got there, yeah, that's cool to think about. Oh, there used to be a river here, or it fell off of a mountain or a glacier. But how does that affect the behavior of the soil now? More so like from the granule side of things. Is it a bunch of smooth little ping pong balls now, size particles that roll on top of each other really easily? Could it potentially be a low spot where it's just been building sediment and sediment over time and over time, and it's very soft and we can't really build on it like a swamp? So start thinking like that. Like, yes, a lot of this stuff is going to be background information. A lot of this is going to be refresher, but now start thinking about how it points to the engineering behavior or the strength of the material. So I said this last class, but geotechnical engineering, the formal definition, according to me, is the science that explains mechanics of soil and rock and its relationship to design, construction, and operation of engineering projects. And again, the mechanics portion, which is why I really like teaching mechanics of materials, is because like we're taking a physical thing that we can observe and assigning a mathematical relationship to it. Why would we assign a mathematical relationship to it? Things. What's the benefit of doing that? It's easier to communicate it. Yeah, it's easier to communicate it. Math is like the universal language.
To test it.
Yeah, yeah. Well, what's 2 plus 2? What's, if you did that tomorrow, what is 2 plus 2? Yeah, so it's a constant. It's always can be predicted too, right? So like if we assign mathematical, if we go assign mechanics to it based off of actual evidence, then that means we can use this as a prediction tool too. So instead of just assuming, well, I know if I put a building on this soil, it's probably going to sink. We can actually measure and predict the amount it's going to sink or the amount it's going to tilt or something like that. So that's the benefit of that, long story short. So we all already know, and I've already shared the little fun map with all the cool colors on it, that soil and rock formations vary across the earth and across the state and across Jacksonville. I'm going to share a few things just here in Florida, specifically of the geologic past that makes our soil formations in Florida like an issue or potentially interesting in certain ways. So in the same way we look back, blah, 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 physics stuff, like in the same way we look back to improve human existence, we look at the history. Engineers need to have a good understanding of the geologic past before we build things on it. So that goes all the way back to like long, long ago, like prehistoric times, as well as current use. You know, in the 30s and the 40s, was there a structure there? Did JA use it as a landfill, or, you know, just the different history from a humankind standpoint as well as a pre-humankind. So there's a few key things that geology gives us as engineers and why we would need to know this stuff as an engineer. Just make sure I'm consistent with all my stuff. So geology gives the engineer some insights on regional conditions. So basically, when we say regional, we mean like Northeast Florida or the Panhandle or South Florida. I'm not talking about like the 1800 block of Beach Boulevard. Like geology is a very, like the study of geology is all based off of regional or large scale conditions, not specific site conditions. But some of the insights are like, you know, what we'll be talking a lot about is like soil and rock types, differences, and consistencies. So is there a rock there? What type of rock is it? Is there soil there? What type of soil is it? Did there used to be a river running through here and that might cause different types of soil, so on and so forth, more on a regional scale here. But please underline that regional portion of it. We cannot use geologic maps. We cannot use the insight of geology for a site specific, right? It's not, it can never replace a subsurface investigation. So the other thing that it can give engineer is information on the deposition or the formation of soil. When I say soil, I mean rock too, but I'm just dealing with Florida, where there's mainly going to be superficial soil. Only in a few key places do you have rock at the surface. So what is it like when I say deposition? Are you guys familiar with the term deposition from a geologic sphere? What was that? Deposit. Yeah. So like, how did it get there? Right? Like has anyone heard of the term alluvial before? It's always a fun word to say, alluvial, fluvial. Okay, so these are all basically like this soil particle, how did it get to its current spot? You know, we know that soil is most likely going to be eroded away or weathered from some type of parent rock. So what happened to this soil deposit from its rock state to its current soil state that we're used to? So the deposition is a type of thing that we'll cover. And then what geologists do is they classify those, or they should say categorize those into various formations of soil. And the formations of soil are all a way of standardizing communication of different behaviors. So a certain formation of soil here in Florida is known for XYZ characteristics. So an engineer, if I hear this formation, like for example, the one we're going to be talking about, Hawthorne formation. If I hear the word Hawthorne formation, then certain characteristics come to mind, just like an engineer working in Miami-Dade County, if they hear the word Hawthorne formation. You know, it's ways of categorizing and lumping in certain characteristics there. The other thing that geology gives the engineer is an insight on potential geohazards. So this is, if you remember last class at the very end, kind of shared some of the different types of specific geohazards like liquefaction, like quick clay up in Norway, and then that also salt dome sinkholes down in Louisiana, those 3 little videos I showed there at the end. All of that information would be known by the geologist. So if you just come into an area and you're a geotechnical engineer, one of the best things to do is to first find the oldest and the oldest geologist and the one who has the whitest hair, and go buy him or her a beer, and just learn from them, because they're going to have all the regional insights. They're going to know that this area on the other side of A1A used to be this, and now we have to deal with that, and all these things that aren't documented that you can't find just through a Google search. So there's a lot of colloquial knowledge that is in geology that is important for us. So I'm just going to show you these, especially here in Florida. So sinkhole prone areas. So there's some areas of Florida where there's a lot more sinkhole vulnerability than the others. So a lot of times people just think sinkhole, and that's a full Florida problem. And especially when you buy a house, everyone's going to be calling you and be like, hey, you need sinkhole insurance. Some areas experience 0 sinkhole formation in Florida. Some areas experience a lot. So just based off of the geology, it could be across the street, and it can be a completely separate thing. So because of this, almost all geotechnical engineering reports will at least start with some type of background of geology and or soil type. So luckily, if you're not familiar with it, there's this big federal organization called USGS, United States Geologic Survey. Has everyone heard of that before? At least. So United States Geologic Survey, and then it's broken down. We also have Florida Geologic Survey that's now kind of partnered with the Florida DEP. So if you're not used to dealing with their websites or dealing with their permitting side of things, once you start working, that's going to be one of the things that you're going to have to deal with a lot, just working through the DEP and the FGS. But they have a lot of background information on statewide Florida geology as well as soil type. And through this class, you're by the end of it, we're going to be very familiar with those online GIS portal tools that allow us to get a general insight of the geology of the site. Before we start building on it, or before we even do a subsurface investigation. And these are all components of that geotechnical engineering report, which we talked about last time is the main thing that consultants, us as engineers, will provide. Okay, so this is one of those recap things that is on the FE. And that's just kind of a fun thing to learn about, but also from an engineering standpoint, it's just mainly so you don't sound dumb in front of geologists. So that's the main reason why we share this. Has anyone heard of or like remember learning about the geologic time scales? Like the 4 units of age, we have eons, we have eras, we have periods, and we have epochs. So the little scale here is shown on the left. Basically, the units of age, it's a scale, but the best way to think of this is like measurements of time. So similarly, how we have like, you can measure time in years, or you can measure time in minutes or seconds. Like it's the same thing. But what they define these eons, eras, and periods of ages like basically in different categories from current present day. So it would be like saying like, oh, the morning hours, like defining the first 3 hours of the day being like gone, or like the last hour of the day, we're finding this as golden hour or something. I don't know. You know, that's like how they would define this here. So the way you would read this, which might be a little tricky, eon is the largest measurement of time or largest measurement of scale. And what we have is a Phanerozoic eon. That's the one we're currently in. So we're currently in the Phanerozoic eon. That dates all the way back. So this is present. Oops. This is all in million years ago. So this little time scale right here, million years ago. So the Precambrian was the last eon, and that was 542 million years ago. So way before I was born and before anybody else was born, obviously. The other one, eras and periods and epochs. These are all following here. You've probably heard the term Holocene before, if you like that one. Indie dude, Bonneville, or whatever you call them. So that's the current epoch that we're in, and that's only from now to 10,000 years ago. The best way I think to like kind of get a grasp of this, because this all seems like a long time ago, but a soil deposited in the Holocene epoch is a lot different than a soil deposited in the Paleocene epoch. Even if it seems like a really long time ago for both of them, you know, like 0.1 million years to 30 million years, still we need to think of it in terms of the scale to each other. So what I did, just real quick, I made this into what I'm calling the smartphone scale. The year was 2010. I got my first smartphone that had Instagram on it, just graduated high school. Oh, it was the best. Like brand new, just came out with a new album, and there was Warped Tour was still a thing. Anyways, so the 15 years ago, the current, if that is our eon, so this thing here for 543 million years is now condensed into 15 years. So that means our current era would only be 16 months. So that means this Cenozoic era that we're in would only be 16 months. So much longer. We're going from 15-year time scale to then just a little over a year. Our Quaternary, which is the period we're in, would only be 15 days. And then the Holocene would only be 3 hours, so the last 3 hours. So this may not make any sense to you, but hopefully for some of you, that kind of puts into perspective the scaling of all of this. So when, again, the whole thing that we're talking about is like for Florida, a lot of our soil is deposited up here because we're relatively young. You know, we might have a little bit of Miocene, might have a little of Oligocene. But if you want to work out west, if you want to work in the petroleum industry, if you want to work in like the nuclear industry too, then a lot of stuff you're going to be dealing with is this era things, these periods, like much older sediment, which has a completely different behavior because it is so much older than the stuff that we're dealing with here in Florida. So just for an example, specific to Florida, again, I mentioned that most of the time in Florida, we're dealing with stuff that's much younger. There's a big thing that happened here that we'll talk about, like why this can change the behavior of Florida or of soil in North America. So back between the Pleistocene and the Pliocene, this is where the max glacier extent was in North America during this Pliocene. So that's what defines it. And although that didn't affect us much here in Florida, if you were to go and work in any of these states up here, then what you'll see is there's a clear difference in geology and currently the soil conditions, as well as the behavior of the soil, just based off of this line. So they could actually use the soil conditions to test the history and know the extent of this glacial formation, because it wasn't like posted on the internet back then, like glacier stopped here, you know, they had to actually go backwards a little bit. So the different glacial advances are here, like whatever they're named after all the Midwest states that you guys have probably flown over before. But it is kind of cool. Like if you look at a geology map of Ohio or Pennsylvania, or if you're familiar with that area, you'll see the soil sediment changing right here. I don't know where Happy Valley is. So I'm trying to remind everybody. Center of state. So let's say you're right here eating homemade ice cream and going to Penn State. And then you move up to Scranton, which I'm assuming is like up here or something. All right. Yeah. And you're watching The Office and Thunder Mifflin and all that stuff. The soil conditions are going to be completely different just because of this extent of the glacier there. And what this produces is what is called an over-consolidated soil. And nobody has probably heard that term, and that is okay. We'll talk about what that actually means later. But in geotech space, this is a very completely different behavior of soil compared to a normally consolidated soil. So it's pretty wild. Like you can literally just drive, 10-mile difference and the soil conditions will be completely different. Your design of analysis of foundation is going to be completely different. Your issues that you're going to have to be dealing with are going to be completely different too. So it's all geology based, and you don't really get this in other disciplines aside from like tsunami or flood warnings as well. So a few other things. So that's kind of the grander scale of it. That happened in that time. A few more important things specific to Florida. So way back here between the Eocene and the Paleocene, this is when Florida was underwater. Is anyone from like Tampa, Peace River area and stuff? You can like find like megalodon teeth in Bone Valley, all that stuff. Yeah, so this was a result of that. So it was underwater here, and then boom, Florida came up out of the ground, and there's palm trees and tourists and stuff. Just kidding, not yet. A bunch of landmass emerges. And then because of that, then it went back underwater. So Florida's geology is very unique because it was exposed, dried up, and then underwater. And then this constant repeat of underwater landmass emerged. And that's all because of the glacial extent moving all the water up there. So what this actually means for us as engineers is it used to look like this. In the Eocene, everything was underwater. So we had a lot of our carbon, a lot of our marine life dying and building and then cementing on top. And that's where we get our limestone starting to form. And then as soon as the Miocene comes up in this one little stretch of land here, this little high point area, we have a lot more like plant life and a lot of other things coming up, and where you didn't have that in the southern portion of Florida. Also, since it was a shallow reef, we had a lot more marine life coming in and depositing different, dying off and creating different like layers of sediment as it was dying over this time. And so because of that, the geology of Florida in that area looks completely different. And because of that, in this section right here, we have a formation called Bone Valley Formation, where there's a lot of fossils, there's a lot of just weird things mixed into it. And currently it's 100 feet below us, but back then it was because it was an exposed shallow reef area. This is also where the phosphate mining really is. If you're from Tampa or that area, you've probably seen those giant gypsum stacks. But phosphate mining is Florida's biggest exporter. I don't even know, just the biggest thing that we do besides like oranges and sunburns and stuff. So like there's like a lot of history in that just because of there. And if you were to go up the state a little bit to Claremont and Ocala and Lake Wales, you look completely different because of that landmass that used to be up there. So one of the issues that we talked about is this interesting geologic history has formed what we call this Hawthorne group of clay in soil, or in Florida. And even if you're not working in geotech right now, as soon as you start working in geotech, you will hear this word Hawthorne group within the first like month or so, if you do any work in there, just because it's this infamous formation that has been reworked, and it has a lot of clay, a lot of silts, a lot of sands mixed in. It's very hard to define. And it's right at that layer where we want to start building our foundations, our piles. We usually try to tap our piles into that. But even if you aren't working in geotech, like once you start working, I guarantee that your geotech consultant or your owner is going to call you and tell you something about this formation. It's kind of Florida's like infamous soil group of clay. It's super hard to define and it's super hard to construct. It can be very strong, it can be very weak, but it also is what gives us our Floridan aquifer. It filters the water as it flows vertically and makes it so our Floridan aquifer is super clear and really clean water that we can drink. So it kind of has both sides of it. Okay, so that was a little history of Florida geology, and again, like thinking about these things, we'll recap a lot of the different like soil formations in Florida as throughout it, but just thinking about like how it got there is an important aspect of it. Geologic formations, I'll go over these really quickly, because we have to cover them because it's a learning objective here. Is everyone familiar with these terms before? These brand new terms? Okay, so everyone passed the 5th grade. That's good. So igneous rock is obviously cooled magma. And the reason why we care about this, if you're designing a rock, like all these rocks are basically the same. When it comes to the soil produced from these rocks, we can have different properties. The clay that is produced from these rocks has different properties. So the igneous is a crystallization of magma. Some of the really dense igneous rock would be our like granite rock, which we use a lot for like roadway ballast and other types of really high strength concrete. Some of the lower ones, obviously, I'm sure living in Florida, everyone's heard of pumice or lava rock. I'm sure everyone's had this in their front yard as landscaping stuff. And when it rains, it floats up and everyone, you're like amazed at your grandparents' house during thunderstorms and stuff. So like pumice, we don't use as an aggregate aside from landscape because of the density and because of the strength, right? So if pumice also in some areas may produce a silt or a clay that is highly compressible, and we don't have natural pumice here, so it's not as important. Let's say you get adventurous and you want to go work over in Greece or over in the Balkans or something. There's these formations of a clay that's produced from this igneous rock. And if it's cooled very quickly, then and the gas does not escape, then it has this clay that's very compressible from pumice. If it cools very slowly and the gas can escape, then it turns into granite. So just knowing you can have two of the basically the same thing, or sorry, two of these very different things in the same area. So knowing like how it was formed is going to be important if you work in that area. Sedimentary rock, this is what we have in Florida. As I'd said before, the layering or the cementation of erosional debris. So it could either be from rivers, it could be organic material, crustaceans breaking down, calcites forming. And the most common one that we use here, all of Florida basically is a limestone. And different types of limestone, coral reef that's been compacted and slowly cemented. Down south, if anyone's familiar with like just north of or south of St. Augustine, you even have like cemented shell hash and cemented beach. It's our artificial reef and stuff, or not artificial, but real reef. But there's different formations off the coast too that is just cemented from wave action over time and the deposition of different marine life. And then eventually you can either take igneous or metamorphic and you just squeeze it a lot with intense heat and pressure. And this is where you get the different minerals that are associated with that. And a lot of times, sometimes these minerals can be reworked into igneous rock or reworked into sedimentary rock. Very like common here. What we'd have is something called gneiss, which is spelled with a G. It's kind of weird. This is when igneous rock is reworked, granite is reworked with a metamorphic rock, or the other side would be like marble or chert. Sorry, that's not an arrow. And this is where limestone is starting to work back into a metamorphic rock. So there's some areas in Tampa where you have really, really old limestone that is starting to get these little like nodules of chert or marble. So there's some areas you might be drilling or looking at boring reports and you'll see, all right, you're drilling, it's all weak limestone, and then you hit this like 2-foot seam of marble or chert of some type of like really dense metamorphic-ish rock. And then you have to decide like how much strength is this going to get it? Is it just like kind of an anomaly, or is it actually part of like the grander formation? Do you have a question?
Oh, no, I was values of the ice because I can't really read it.
GNEISS. Thanks. If anyone's ever been to like New York Central Park and stuff, all those rocks in there, I'm pretty sure that's what that is. So you can impress your friends next time and say nice. I'm sure your friends would all applaud. Okay, so that's the mandatory rock talk there. In Florida, though, what we care mainly about is the soil. And this is a soil composition like lecture, so we're going to be talking a lot about soil. You may have heard the stupid old like saying like, oh, geotechnical engineers don't like the word dirt, don't use the word dirt around geotechs. And it's a super old saying, but it's 100% true. So do not ever say that. No, I don't care. A lot of like the older guys will care about it. For the purpose of this class, the reason why we use the word soil is because we're talking about weathered rock, organic matter, nutrients, water, and air. So more holistically, everything that could potentially be in soil underground. You could have organics, you could have different types of gases, you could have obviously water, different types of water. Dirt is usually just associated with like once we pull it out of the ground and we're trying to sell it, or Florida Georgia line, that stupid song that is yeah, you guys know about that one. So you just know, like, usually you'll hear a lot of geotechs and geologists call soil or sediment. That's when we're talking about in situ under the ground. So again, if you want to sound smart near them, then use that term soil. Don't call it dirt under there. But the things that we care about is the weathering, like how it got from a rock from its formation originally to where it currently is. So we know there's 2 types of weathering. There is physical, and then there is chemical. And physical weathering would be from wind and water, or from abrasion. I think I spelled that wrong. Which is from the glaciers, or glaciers, as we say. So yeah, I mean, you guys have heard these before, right? Like the different types of physical weathering. The chemical weathering would be from like chemicals, acids. So a lot of times we could have rainwater or acid rain, or groundwater. Or this fun word I'm gonna put here if I can spell it. Anyone heard this word before? Anthropogenic. Oh yeah, that's a fun word to learn. It will definitely impress friends. It's anything man-made. So like anthropogenic is something that like anthropology, study of humans. So something that humans have caused. So like it could be installing cast iron pipe that then is leaching and changing the groundwater, and then like changing the chemical balance of the water, and then causing different types of erosion there. It could be, septic tanks or something like, a lot of times now, especially since we're seeing this infrastructure in place for a while, we're learning the consequences after the fact of it. So physical and chemical weathering is important. What I'm going to start with here is the post-weathered terminology. So once we have this weathering phenomenon, whether it be physical or chemical, how it gets from the parent source to the current spot that it's in tells a lot about the engineering behavior or the types of mechanics that are associated with it. So the most common one, or sorry, not the most common one, the one where like that we're going to start with is called residual soil. So residual soil, residue is like a lot of stuff like leftover, right? If you think of residue leftover, Residual soil is when the rock is weathered, but the soil, the resulting soil doesn't go anywhere. So like an example of this would be like if in some areas in Florida, we have limestone and there's no running water, there's nothing, but over time, like acidic rain or just like organic composition, the CO2 in the atmosphere will break down the limestone. And the limestone will become lime silt, or it would turn into weathered limestone and lime silt, and it'll just stay put where it is. It's not moving anywhere. Another really common thing is in like South America, Bolivia, and in like in the capital of Colombia, they have a lot of residual soil that is actually like old igneous soil or like igneous sediment that is now like washing away underground due to the aquifer, but still like staying put, you know. So in Florida specifically, like an example of this would be like limestone to weathered limestone to lime silt. Where yeah, it's not necessarily moving, and we're just talking about like time here between each one of these. So what the time is, it could be years, it could be decades, it could be hundreds of years, it could be centuries, it could be millions of years. But a lot of times it's something that you'll hear engineers talk about, like, oh, this area is full of residual soils, or it's hard to define the mechanics of these specific type of residual soils in Gainesville or something. So that's kind of like that first part where it's post-weathered, but it hasn't moved at all. Now, most of the time, though, especially since we're dealing with geologic time, there's going to be some factor, some influence that has caused sediment to move from its initial spot to where it currently is. And this is where we get into all of these really fun names here. So these are going to be a category of transported soils, and this is obviously where the particles are sorted by the size, by the deposition, based off of the transportation, shape, compaction, composition. It can all change here. So if it's transported by wind, what it's called is an aeolian. Let me make sure I spell it right. Aeolian sediment. So again, these words may never be familiar with you, but if now once you hear them, you'll probably start seeing them pop up, especially throughout the semester when we start diving into the geology resources a little bit more. So this is deposited by wind. A lot of like beach sediment up in the north, like the dunes and everything, like those are deposited by wind. As you can probably imagine, if I have a stack of soil right here and I put on a fan and I blow it this way, what type of characteristics might be of this soil now that was just blown by the wind? Like if it's sand. Say it again, surface level. Yeah, so it might be thin, it might be spread out. It's very loose usually. So like if it's a loose sand, aeolian sand, it's not compacted, it might not have a lot of strength. So these are some of the things that we might have to consider. Usually it's going to be pretty well sorted because the wind is going to be blowing at a certain speed, which only picks up a certain like size of particle, right? Like, so like maybe the heavier, the more dense, the larger particles are still here, but now we just have like a uniform smaller particle over on the aeolian sediment, which might be good. It might allow water to flow through it a little bit easier if it's uniform, but also then it's harder to compact. It's harder to build things on because it could shift a little bit. You know, like having a bunch of things the same size as ping pongs or same size as a bucket of marbles. Like it's going to roll around a lot. It's not going to interchange each other. So aeolian sediment, there's not a lot here in Florida, but again, up in the Great Lakes area, you might come across some of this aeolian sediment. Transportation method, if it's transported by sea or if it's deposited in salt water, then this one's really nice and easy. We call this marine sediment. So does anyone remember that formation I talked about in Florida? What was the name of that? Hawthorne. Yeah, the Hawthorne group, that's a marine sediment because it was deposited in a shallow reef in the section where all the sharks were coming and dying, all the coral was coming and dying. It was just deposited over time. So a marine clay or a marine sediment, that is one that is associated with a deposition in sea, whether it's currently in the sea or not, because now the Hawthorne group is not in the sea. So it's not the current state, it's how it was deposited. Another fun one here. So if it was deposited in a lake, this is called lacustrine. You can kind of remember that based off of lacustrine sediment. We don't have much of this in Florida because we don't have like lakes that are super, super old. But some sediment, especially in like Africa and like in Russia and stuff, if you ever end up working there for some weird reason, there's a lot of lacustrine sediment, like areas where they have like larger lakes that have been collecting sediment. The one that's really common that you've probably heard of before, or if you haven't, you will. Fluvial is from rivers, so think of it like flowing. Rivers are the things that transport the most amount of water, or sorry, that transport the most amount of sediment in soil. So even though we don't have any or the main river in Florida is St. John's going up. A long time ago, we used to have a lot of rivers from the Appalachians flowing in through Florida. So we actually do have a lot of fluvial sediment, especially in Orlando, where like a lot of those rivers terminated. So rivers, fluvial sediment can be very specific based off of the path of the existing river. And it's usually a pretty like nice and dense material because the rivers are going to be transporting, everything, and not like wind that might just be blowing a few things. So ice, or for the glaciers here, this is either called glacial or glacial if you're everywhere else in the United States. Another term here is moraine. So if you ever done hiking in like Wyoming or I don't know, anywhere like up in that area, Montana, where there used to be glaciers, a lot of like parks are named after that moraine. There might be Moraine Lake or like a moraine prairie, and that's just something that's formed by a glacier. Glaciers are pretty like gnarly when it comes to sediment because basically they're just bulldozers that push everything and then just stop and just deposit it all. So in areas with a lot of glacial or marine sediment, it could be all nice sand, it could be all nice silt, and then like 30 feet down, you hit like a 40-ton boulder just randomly. Like it's all like kind of like reworked, just re-scraped and deposited as it is. So in areas where you're doing a subsurface investigation in glacial sediment, it's really important to like cover your bases and ensure you're not, building on something that might have, especially in excavating, like you might hit some like really large rock, some really hard things to get out of the ground, where marine and lacustrine and fluvial might be a little bit more consistent. All right, the last one, if it's deposited by gravity, which you could probably imagine not much here in Florida since we don't have a lot of hills or mountains, this is called colluvial. So this is very common in other places where you have more isolated pockets, like in Iceland and other areas where you have a younger sediment that is deposited by gravity. So stuff falling off of rocks over and over again, or stuff falling off of hillsides or something like that. So this is more so the big picture. On the FE, you might be asked to know some of these. In Florida, most of them are going to be marine or fluvial sediment. So, but again, like if you work any other places, then you're going to have to know these terms, and they might just use it right off the bat. Your geologist or the person in your office might say like, oh yeah, we have primarily aeolian sediment. And then everybody knows aeolian is deposited by wind, or colluvial or marine sediment. Let me just write that here. Okay, so I'd mentioned earlier, like the formations in the USGS. Now, primarily, like mainly what we look at here, the formation that from like a geologic standpoint, like that we'll talk about in a little bit, like the categorization of Hawthorne group or whatever, it has to do with the deposition, but it also has to do with the mineralogy of it. Now, most sand here in Florida is going to be what's called a quartz-based sand. Everyone familiar with quartz? Almost shiny like crystal. I don't know all the chemistry behind it, but that's what the majority of our sand is going to be made of. Sand that is not quartz-based will be a lot weaker. And even though it will look like sand, it might crush a lot easier. So you don't want to use it in structures. You don't want to use it in concrete. So quartz-based sand is that. For clays, a lot of like clay mineralogy is what we call, again, fun word, kaolinite. You guys are, your vocabulary should be like next level. Like if you're into crossword puzzles, you guys will all be pros after this. So these fun words, kaolinite, or this one here, like montmorillonite. They really went hard on that one there. Montmorillonite. Again, these probably and most likely and shouldn't have any meaning to you right now. But as we get deeper into the geotech and deeper into the mechanics of it, we'll see that like a clay that is heavy on montmorillonite, just because of the structure of it, will most likely expand and contract based off of the water differences. So this is really common in Texas, where you have swelling clays. Like in the rainy season, your clay literally like a sponge, like will swell. And if you just built a brand new house on this in the dry season, then you're going to have foundations issues, you're going to have roadway issues, that kind of thing. Kaolinite is more of a steady clay, or more of like a non-reactive clay, where the water changes might not change over time. So like, again, like there's going to be key differences, and I'm telling you all these fancy big words for a reason, because they're eventually going to be able to help us predict the behavior when it comes to the engineering behavior, at least. So most of the time in terms of soil, we have this mineralogy, like the solid portion, but then a lot of times we'll have also organic material mixed into it, especially here in Florida. That's the worst, or like Florida is one of the worst states for organic material, just because of our swamps and the young geologic age of it. So organic material obviously is going to be decaying plants. There's going to be a bunch of microorganisms that might hurt or help our soil. And then, of course, like bacteria too. So what makes this important is like, yes, we're going to define the current state of organic material, but we're determining whether it's aerobic or anaerobic, meaning it has oxygen or doesn't have oxygen, which means it doesn't support or it doesn't have microorganisms, might help us in a decision of what it might be like 50 years from now. You know, civil engineers build stuff that will hopefully be around for a while. So yes, we need to define the current state of it, but we also need to think about what it might be and what the rate of degradation might be. So a lot of tests, and ones that we can't do in this lab, is defining the organic material, organic mass. So like when we talk about organic material, what you'll see a lot of times is we will measure the percent organic content by the mass. Does anyone want to guess like what, like physical, like how could we, if we had a bucket full of soil that had minerals and organic mixed into it, how could we measure the organic content of that soil? What is something we could do to it?
Try it out.
Dry it out? Yeah.
Like filtrations. Sieve.
A sieve. And it could be the same size. And yeah, if you dry it out, that'll get rid of the water, but you're not getting rid of the other things. Oh yeah, we can burn it. So that's what you do. So extreme drying out, basically. So like knowing that, okay, like it's gonna take clay and sand and the minerals, it's gonna be real hot to burn those. So we keep them around like 300 Celsius or something, a little, I mean, only like something less, where you burn off all the organic matter, you burn off all the plants, you burn off all the bugs, you burn off everything else. And you take the mass before and you take the mass after. And that's how you get that percent organic content. I've been like lobbying so hard for us to be able to do this test here and just get like some of those like boring flamethrowers and stuff. But EHS, the environmental health and safety has not gotten back to my crest. So, but that's a very common test that you would be doing in a geotech world, in a geotech like lens, the percent organic material, especially here in Florida. So some of the definitions that you might see throughout it, and different organizations like Florida Department of Transportation, they have different definitions, but like if you hear the words with organics, usually this is like somewhere around 15% organic content, which is a lot if you think about it. Like remember, this is all by mass. So if we had like a softball size of quartz versus a softball size of like a plant, like which one do you think weighs more? Like probably the quartz, right? Like the organic material is like water and plants and everything. So like this 15% is by mass, not by volume. So like if we have 15% of organics in our soil, like then usually it's pretty discernible. Like it's usually like, you know, you can see a lot of organics in there. Muck is somewhere in between. Usually it's between, well, I'll show the other extent here. If you have greater than 75% organics, then usually what we do is we classify this as peat. Anyone heard that? Anyone heard peat before? Any Scotch drinkers in the house? Yeah. Okay. So no. Well, then ask your grandpas about it. I'm sure they've like heard the word peat. That's a very high organic content. Anything in between that 15 to 75%, usually we would classify that as the term muck or mucky soil. And we'll talk more about this once we get into the classifications of that. So one of the things that we look at often as geotechs is the geologic maps. Again, this is the regional insight. So we're not looking at site specific, but they really help give us information on the anticipated soil at the ground surface. So maybe you worked at a geotech office, or you visited geotech office. By the end of this, you guys will all hopefully get a chance to go to a few geotech labs and offices. You'll see these geologic maps are usually like posted up everywhere. Like all the engineers will have them on their desk, or they'll have them in like the lobby or above the urinals or something, just so you can like get used to seeing where all these things are. So what they tell us is information on the deposition and the formation, which now we know. So this could be like, is it alluvial? Is it, is it marine, etc.? So what is the actual deposition? And then also the formation. So again, hawthorn is a type of formation. Some other ones that we'll talk about, Cypress Head is a formation that's in Florida. All these cool names, Ocala limestone. So it'll tell us this information. And the whole reason, again, is so to help us be standardized in the state. Like an engineer working in Jacksonville that has Cypress Head formation up here has a very similar characteristics, very similar mechanics to the Cypress Head formation in Orlando or in Tampa. So like it helps us keep a level of consistency by grouping these categories. The other thing that it'll tell us is the composition. And so examples of what composition means is like the physical, what it's physically made of. So is there a lot of shell? Is it this fun word called clastic, which means it's like a carbonate material that might be very vulnerable to like acid rain or something. Is it heavy on quartz? Is it silty? Oops. So composition like that, what is it made out of? Is it like have a lot of pebbles, that kind of thing? So geologic maps are almost always included in the initial site investigation. So after this class, I will post on Canvas and like in the little thing, like the resources page, I'll post an example subsurface investigation report that like a geotechnical engineering firm, gets paid to produce. And you'll see these maps in there, and you'll see a short discussion about like where the site falls within this geologic map. And again, as I said on the first page, it is also a tool to anticipate potential geohazards. Because a lot of times, some of these geohazards are associated or more vulnerable in some of these specific types of deposits. Like here in Florida, the reason why I said Hawthorne and Cypress Head is because in Florida, like where we have the Hawthorne group and the Cypress Head right on top of each other in Ocala and in like I-4 corridor, basically. That's just for whatever reason, that's where a lot of sinkholes pop up. Like the Hawthorne group and the Cypress Head is just associated with a lot of sinkholes. So, the geotechnical engineer will use these as a tool in their analysis. You will never see a geotechnical engineer just look at a geologic map and be like, all right, boom, I know the foundation design just based off of this. It's always a starting point to better guide your client in what level of subsurface investigation. How many drill trucks do you need? Like how many borings? Do we want to use geophysics? Some of the other ways of imaging underground. So it's always just used as a tool. It's not used as the end all be all. So the most recent geologic map of Florida, and I will post the link to this. This one was formed in 2004. It's very pretty. There's a lot of information on it, a lot of fun colors. But the things I want you to take away here is the geologic map of Florida here shown on the right hand. This is all at the surface. So you might see some key things that look like they blend into each other, right? Like you can kind of see this orange layer that kind of follows the St. Johns River. If you're familiar with looking at the St. Johns River, if you know about the Panhandle, you have Santa Fe, and you have the Swanee River kind of up here. In this area, you have the rivers following different formations, and that's because like the rivers are a method of transporting sediment, right? So we'll usually see these here. Down in South Florida, we see a lot of more blanket sediment because this is a newer or a younger section of Florida where it's mainly going to be just recently deposited beach sand. If you zoom in here, which you can't really see it all, but right here, these give a generalized cross section with depth. So we see it's all Holocene sediment, and then these are the actual geologic eras. So you can see the Eocene is the oldest that we go to in Florida. And if you scroll back to whatever the slides ago, you'll see Eocene was relatively young, compared to the rest of the state. So you can see the different sediments here, and these are all the soil formations. Again, this is super blurry, but it's a high resolution picture, hopefully on your slides where you can look it up. I'll also post the link to this. But you'll see some of those key like formations that we talked about. You'll see the Hawthorne groups. These are all the colored greens there in the Miocene. Those are all Hawthorne group of soils. Some of the other things we talked about, like the different types of limestone or the different types of cypress head. And these are all shown on the map there. The other kind of cool tool here is to show the different cross sections. So again, hard to see, and I apologize for that on this 19-something projector. But based off of well points and different types of borings throughout the state, they've created different cross sections. So from A to A prime here in Jacksonville, and then B here. So essentially, like if the state of Florida was a giant cake and you just like cut it down through the Panhandle or through the peninsula. And this is the generalized cross section of what you would expect to see. On the scale there, it goes down to 500 feet below sea level. So yeah, it'll tell you where sea level is, and it'll tell you to a depth of 500 feet below sea level. So this is all regional, but this helps us engineers identify where the rock might be, where the Hawthorne, where clays might be, as well as the generalized topography or what might change. And especially if you want to get into any mining industry or petroleum industry, you would be using these a lot because there's only certain types of formations that produce certain types of minerals or certain types of formations that only produce certain types of petroleum that we need. So if you look and be like, okay, we need to drill in this area between a depth of 200 and 300 foot in depth. And then you can price your budget that way, so on and so forth, everything like that. So these are helpful tools. Next page, you kind of see these cross sections. I just zoomed in a little bit. A prime here, that's where Jacksonville is. So we would be the tail end here. Very little amount here on the far end. You can actually see this is the St. Johns River right here. So really Jacksonville is just this little section where we have a Hawthorne group, and then under that we have Ocala limestone. And then above that, we just have beach sediment. So those are QU, that's shown as quaternary sands there. You can see the St. Johns River cuts actually into the Hawthorne group, which is why, if you're familiar, if you're ever interested, St. Johns River, like Green Cove Springs, and like there's a bunch of springs actually like underwater that are feeding the St. Johns River. Really exciting. So that's the reason why we have a lot of those in there, is because you have a river actually cutting into this sediment. So yeah, interesting to see how it works throughout the state too, and throughout the panhandle. But of course, this is only a very rough scale of data. Like there's a data at point every county or so. So you wouldn't use this in substitute to an actual site investigation. Okay, so just to wrap up, geologic maps are very important, but they do not provide information on a project scale. So you'll see in geotechnical engineering now that we have better ability, cheaper techniques to capture data. We're going more so on a site-specific analysis. So we're looking at like analyzing like sites as well as specifically like breaking up partitions. Like when we were designing this building, maybe this one section has a certain properties, this one section has a different property, and not more so a blanket end all be all thing. So they will never replace subsurface investigation. So if you're afraid of AI taking over your job, don't worry about that, because we know more about the moon than we do about the soil. Just kidding, I have no idea if that's true or not. That sounds kind of cool, but we don't know a lot of stuff about our subsurface investigation, or like our subsurface. So it's always going to require some type of drilling, some type of investigation underground. It will also never tell us anything about the strength parameters. So it's only qualitative. So there's some inferences that we can make. Like generally we know that like fluvial sediment will be stronger or more dense than aeolian sediment. And generally we know that moraine sediment may be more well-graded or maybe more dense than fluvial sediment, but it will never give us an actual value. Like it will never be able to tell us like, hey, you can build something 10,000 pounds right here on this. There's no strength values according to this. So it will help in terms of mechanics by giving us insights or ranges, but never actual like replace the true mechanics of it. Because remember, the mechanics is the math that is the response of a material to loading, which means we need quantitative measurements. Also known as numbers, or what you guys know as hashtags. So numbers. We need the actual testing, subsurface testing. We need something to truly get a ground truth rather than just estimating these values from like a larger scale. So kind of in summary, this little cartoon like is really helpful, because if no matter what engineer you're going to go in, especially if you're environmental too, you might still have some geologists on staff or even geophysics. They're all within the same sphere of work, so we work on similar projects, but they're all very different. At the end of the day, like, we can all get information from each other, but a lot of times geologists are more so painting a wider scale picture, where the engineers are like, okay, how can we take this information and design something based off of it? But we can't do this by ourselves, because if engineers just work by themselves, then there's no physical meaning behind it. You know, we still need to like ensure that we are taking into account the